Hello everyone, we are discussing the nature of stress strain curve for different material. Okay. In the stress strain curve, we can get various parameters like initial modulus, yield stress, yield strain. Okay. This we have discussed, and the total nature of curves, this stress strain curve we have discussed. Okay. So, this region beyond the yield point. So, after that the due to rearrangement of the molecules. So, this curve again it increases, and the nature of curve depends on the molecular structure of fiber and the fiber structure of yarn. So, if the fibers in the yarn are aligned towards the axis, then stress strain curve will be entirely different than the fibers which are twisted. So, depending on the twist characteristics, the stress strain characteristics will change. Now, let us see different fibers, different yarns, how do they change, how their stress strain characteristics change. So, this is wool, and wool has got this stress strain characteristics, where with the small increase in stress, it gets strain, very high strain. So, it has got very high extensibility. Okay. But on the other hand, flax has got very less extensibility. So, this is mainly due to the difference in their molecular structure. Now, for same fiber, okay, polyester. So, polyester, it is a low oriented polyester, partially oriented polyester and fully drawn polyester. Okay. So, in case of same fiber, if we can orient the molecule, okay, the stress strain curve will totally change. So, this is basically a low oriented polyester, as we have discussed earlier. This nature is mainly due to rearrangement of the molecule. Okay. So, molecules get straightened, aligned towards the axis. So, during that time the strain is very high. Okay. But in case of fully drawn yarn FDY, it has been aligned, oriented. So, that is why it takes higher stress with smaller strain. Okay. So, rigidity of that FDY is much higher than LOY, okay, which is expressed by initial modulus. Now, another example where normal cotton is treated, chemically treated. After chemical treatment, both stress and strain normally changes. So, here it shows the cotton becomes weaker, okay, and it has got its the lower breaking stress. Okay. So, the stress strain curve also changes with the chemical treatment. Now, as I have mentioned, with the increase in twist multiplier for staple yarn, it gets changed, the stress strain curve, stress strain characteristics get changed. Now, here we can see that in green curve it shows it is a say normal yarn, okay, normal yarn, and with the increase. So, here it is this is the characteristics, and when the twist is increases. So, TM to TM, this is TM1 which is lower, and increase to TM2, twist multiplier 2, then twist multiplier, it is the highest TM. So, as the twist multiplier increases, the fiber, the yarn become stiffer and stiffer. That means, initial modulus is increasing, because the fibers are, they packed together, packed in a better way. Okay. For better packing, due to this better packing, that initial modulus increases, the yarn becomes stiffer. Okay. But that as the twist increases, initially this is the strength increases, this is due to the increase in the frictional contact. But beyond certain point, when we move beyond Tm2 to Tm3, what happens? Due to the obliquity effect of the fibers, so actual final breaking stress drops, although the initial modulus is higher. So, this total yarn characteristics, total stress strain characteristics, looking at the stress strain behavior, one can predict what is happening there. So, these are the different factors which affect the stress strain behavior of textile material. Now, we will discuss another terminology which is called work of rupture, or it is called that the area under the curve. Work of rupture is nothing but the energy required for break, okay, due before its rupture. So, it is a measure of toughness of material. Okay. This is work of rupture is very important for many applications. Like one example, in mountaineering rope. Okay. So, it is not that the strength, the stiffness of the material which is important, which is the important is that how much shock, how much energy it can absorb before it fails. So, that is important. So, there are many applications where the energy required to before breaking, like in weaving, it is not the strength of the warp yarn which is important, it is the work of rupture of the yarn which it is important, because during the shedding and beating operation, the yarn has to actually withstand the energy, okay, energy required to break, that is important, and it is not important that which is the stiffer one or which is a stronger one. A strong yarn, very strong yarn with very high stiffness, that means very low elongation or low work of rupture, like there is two yarns we can talk. This is cotton yarn. Another is suppose steel wear, strength is very high, but stiffness it is very stiff, and here it is say high carbon steel wear. Okay. Now, here if we see the area under the curve, what is the area under the curve? For cotton, this is the area under the curve. That means, energy required to break the cotton fibre yarn will be this one. But on the other hand, if we see the steel wire, the breaking energy required will be this much. Okay. That means, the cotton requires higher energy than steel, although steel is extremely very high. So, the question is which one will be suitable for weaving. If we use the steel wire in as a warp in weaving, it will immediately break, it will start breaking, its performance will be very poor, and as compared to cotton, cotton will do much better performance. Okay. It will have much better performance. So, not only in weaving, there are many other applications like a parachute. In parachute, even in the parachute fabric or the rope, when the paratrooper jumps, okay. So, the work of rupture, that is the energy before it breaks, it has to be very high, otherwise it will fail. Okay. So, in that way textile material has got its advantage. Okay. So, it is the energy or work required to break a specimen. Okay. That means, the area under the load elongation curve, that is area of the shaded zone, that is the work of rupture. Now, we can see the animation here. This is the load elongation curve. We must be very careful. This is the area under the load elongation curve, not the stress strain curve, because it is the energy, okay, load and that is force and multiplied by the elongation, and this is the work of rupture. Okay. So, area under the load elongation curve. Now, what will be the unit of the load, unit of work of rupture? So, unit of work of rupture is the gram force multiplied by centimeter. That is force multiplied by distance, that is the work of rupture. But for practical purpose, for comparison purpose, what we do, this is the work, okay, because W is proportional to the cross section, okay, denier. W is proportional to denier and also its a length. That means, if the denier is higher, it is a denier, it is a coarser denier or coarser tex, then it will be the work required, force required to break will be high. Okay. That is why the W work is proportional to the denier, and also as the initial length of the specimen is high, then the work requirement will be high, because that extension will be high. So, that work of rupture will be high. So, the work of rupture is actually, it changes with the denier proportionally and with the initial length. That is why for comparison, if we divide these things with the denier and centimeter length, in that case, like we have seen earlier, the stress is divided by the linear density, the gram force is divided by the tex, just for comparison purpose, that we have seen. Here again, if we divide the work of rupture by denier and the length, so that we can compare. Okay. We can compare the and if we rearrange this equation, then the centimeter will be cancelled out, ultimately will remain, it is a gram per denier or gram per tex. So, if someone says that okay, what is the practical, the unit of work of rupture, it will be gram per denier. So, effective unit will be gram per denier or gram per tex for comparison. Okay. Next is that work factor. Now, work factor, the concept of work factor is just to understand the nature of curve. The curve can be any textile material, the curve can be like this or can be like this. Okay. So, for a very stiff material, the curve will be initially it will have higher stress, this is the stress strain. So, initially it will take higher stress, then gradually it will break due to the bond breakage and all this, it will have another like wool. So, initially there will be extension, then it will increase. Okay. And there is a ideal curve which will increase with the, say there will be straight line, that is ideal material, okay. That is elastic material which will straightway increase, although the textile material will not follow this one, either this will follow this type of curve or this type. Now, the work factor gives an idea, by if we know the work factor value, it gives an idea about the nature of curve, whether the curve is following this type pattern or this type pattern. So, always we do not have the curve in front of us, but if we have the work factor value, then we can tell it is the nature, we can actually guess the nature of curve. Now, let us see the animation here. Now, this is the ideal curve, okay, where the work factor is nothing but the area under the curve, this area under the curve divided by breaking stress and breaking strain. This is the breaking point. So, what is the area under the curve? Area under the curve is half of breaking stress and breaking strain. So, this is the area under the curve, half of the this base and altitude. Okay. Altitude, half height is that stress and base is the strain. So, and divided by the breaking stress and breaking strain. So, in that case if it cancelled out, so it remains half. So, work factor will be half in case of the ideal elastic material. Okay. Now, another material where this is the there is an increase in this. So, here work factor will be, what will be the work factor? Because area under the curve, area under the curve will be more than the this straight line, the actual area under the curve will be more. Okay. So, and divided by the breaking stress and breaking strain. So, that means the work factor will be more than half. Okay. And on the other hand, if we see the other type of curve, it shows with the blue line. So, this is the curve where it is a work factor, here it is a less than half. So, the by knowing the value of work factor, we can guess, we can actually predict the what type of nature of the curve. Okay. So, if the curve follows Hooke's law, okay, the material follows Hooke's law up to the breaking point. So, there is no bend, then the work factor will be half. So, it is area under the curve divided by breaking stress and breaking strain. Okay. And it describes the nature of the curve numerically. Okay. It is not, if we do not have the curve in front of us, but numerically it is, if it is the value, then we can guess, we can tell the, okay, this is the work. So, work factor of 0.4, if it is asked draw stress strain curve of a material with work factor of 0.4. So, in that case you have to draw curve like this 0.4, okay, work factor of 0.4, okay. Straight line work factor of 0.5, work factor of this 0.6. So, this type of actually problem it is given in the exam. So, it is given that the curve, nature of curve, different nature of curve, and tell the work factor, whether it is a this 0.4 or some values will be given, we have to tell the work factor, predict the work factor, okay, logically. Now, the term elastic recovery, what is that? It is the property of a material by which it tends to recover to its original size. Okay. So, any material after extension, it normally it tries to recover to its original size and shape, okay. But there it may not be 100%. So, by the term elastic recovery, it is actually one can see, one can actually calculate the how much deformation it will try to gain to its size, original size and shape. Okay. Now, this is the yarn. Suppose yarn, initially the yarn length is AB, AB is the initial length. Okay. Now, it is a load elongation curve. Now, we are extending from B to D, we have extended, the load has increased. Okay. This up to this point we are not breaking the material, and after that we release the material. After releasing, its load is gradually reducing, okay, and then it is reaching up to the point C, it is not coming to the original point. Okay. So, this is the deformation, it is called plastic deformation, okay, and this is the deformation, it is called elastic deformation, okay, where it is recovered. Now, we can see the animation here. Now, it is increasing. See, this is the initial length of the material. So, suppose it is yarn, AB is the initial length. Now, it is extending and it is increasing and it is reducing. Okay. Now, this is the distance we can calculate. Now, AB is the original length, AB original length, CD okay, is the elastic extension, CD is the elastic extension where it is come back, and BD is the total extension from B to D, it is a total extension, and BC is the permanent set, okay, that is plastic deformation was there, and from there one can calculate So, elastic recovery is the CD, what is the recovery divided by total deformation. So, CD by BD, and for perfectly elastic material there will be total recovery, that means BC will be 0. So, BD will be equal to CD, that means BC is 0. So, in that case for perfect elastic material elastic recovery will be 1, and for perfectly plastic material that means CD it will not come back, it will remain at that point, okay, that it is called at it is 0. So, elastic recovery is 0. So, textile material, most of the textile material they are neither the plastic material nor the elastic material, they work on the viscoelastic. So, it will actually come back, but it may not, it will, there will be definitely some deformation. Okay. If it is extended beyond the yield point, but if it is extended within the Hooken region, then it will come back. Okay. That is why for most of the low stress mechanical characteristics it works under within the Hooke's zone. So, this is AB is the original length, BD is the total extension, CD is the elastic extension, CD is the elastic extension, that means it is recovering, and BC is the permanent set, and elastic recovery is CD by BD, CD by BD. Okay. For perfectly elastic material this BD will be equal to CD because it has come back. So, BC will be 0. So, perfectly it will recover. So, elastic recovery is 1 and for perfectly plastic material that is its a CD is 0. So, elastic recovery will be 0. Okay. So, there are different applications not only in technical textiles, but in the daily apparel also, that bagging effect of garments, okay, dimensional stability, it changes with the stress characteristics. So, this even with the different technical application, so we must know the elastic recovery characteristics. Next is that, so we can calculate the yarn specimen, okay, of 200 millimeter extended by 10% when loaded with 500 centinewton force. Okay. That means, when 500 centinewton force is applied, okay, the 200 millimeter yarn is extended by 10%. Okay. The length of the specimen after removal of load was found to be 202. So, after removal there is a deformation, that is it is length 202, that means it was initially 200, now it has become 202. Calculate the percentage elastic recovery of the yarn. So, 200 was the initial length and extension was 10%, loaded 500 by 500 centinewton and final length is 202. Okay. Here the load value is not required because extension value is known. Okay. So, extended length will be that is 10% of initial length, original length. So, 10% of original length it has increased. So, it has become 220 millimeter and the final length has become its a, that is the total extension is 20 millimeter and elastic extension is that extended length by final length. Final length was given. So, elastic extension was 18 millimeter. So, 20 millimeter is the total extension and elastic extension is 18 millimeter. That means, the ratio of these two will give us the value in percent, okay, multiplied by 100. So, it has become 90%. So, 90% elastic recovery is there. So, one should practice this type of numerical, this is the answer. Next is that time dependent effect. Okay. So, time dependent effect is that, so here its load is not increased continuously. In earlier stress strain we have seen stress is load is increasing and strain is taking place, but here the material is loaded once, okay, and it is kept at that loading condition for a long time. So, this type of situation is there in many technical applications, like in geotextile, for any application where the material is under constant load for long time. So, for that we must know the stress strain behavior, okay? The strain behavior, time and strain behavior. What is that? Load is fixed, that this is for geotextile under the ground it is continuously loaded. So, we must know the its strain characteristics, so that we can predict whether it will fail or not. Okay. So, that characteristic is that time dependent extension, it is known as the creep. Okay. Now, once it is loaded, there will be two types of extension. Suddenly we are hanging a constant load, it is not that load is increasing continuously, increasing at certain rate. Okay. Suddenly we are hanging certain load. Okay. Here as per this curve it is loaded. So, during that time there will be one instantaneous extension. This is the zone where the material will get extended instantaneously. Then after that it will not stop here, it will keep on extending. Okay. So, if we see in normal load elongation curve, for that particular load value the extension could be like this, could be up to this point, this is the extension up to this point. Okay. But if we let the load remain for long time on the material, it has been observed that there will be again continuous increase in elongation, it will keep on elongating. This elongation is known as the time dependent elongation, is known as the creep behavior. This is due to the molecular rearrangement, okay, of the, and after that, after certain time, if we release the load, okay, again it has become 0, and it is not that immediately it will come back. So, it will try, it will come back slowly. Initially there will be immediate response, immediately there will be sudden drop in strain, suddenly there will be contraction, but gradually it will come back, try to come back, but after certain time there will be no reduction in shape or size. So, this difference is known as the permanent set. Okay. That is due to, that means there will be permanent deformation in the molecular structure. Now, we will discuss one important factors, some important factors which affect the tensile result. Okay. The tensile result means that for same yarn if we change same textile material, if we change these parameters, the value, load value will get changed. Suppose there is a yarn, this is a yarn. Okay. Now, the yarn cross section, its unevenness will definitely be there. Now, yarn will break in its weakest point. Now, if we can plot the yarn, the strength, theoretically if we can get the yarn strength at different point, okay, the strength of the yarn will be like this. At different point the actual strength will be like this. Okay. So, this is say S1, S2, S3, these are the weakest point. And now, the it is a specimen length. We can test the tensile test by, this is the yarn sample, this is the top jaw, this is the bottom jaw, and here suppose it is a length L1, length L2, length L3, like this. Okay. If we take this, the strength, if we measure the strength of yarn by taking this total length, by taking the total length which is L1 plus L2 plus L3. Now, if we take suppose this is the top jaw, here it is a bottom jaw. This length is the, it is called, it is L 1 plus L 2 plus L 3. If we take this length, so here as per this picture S 1 is less than say S 2, okay, is less than S 3. So, S 1 is the lowest value, followed by S 2 and S 3 is little bit high. Now, if we take the gauge length as L 1 and L 2 L 3 a total length, if we take, in that case what will be the strength of the yarn? The strength of the yarn will be S 1. If we take, that means, in this case the strength of the yarn is S 1. Now, if we take the yarn, another test if we do, if we perform, in that case, so here another it is test 1. Another test if we take, that we are now trying to break, we are trying to reduce the size, reduce the specimen size. So, this is L 1, L 2, L 3. Okay. Now, if we test the L 1 here, this is L 1, what will be the strength? Again the strength should be S 1 lowest. Now, if we test the say L 2, then the strength will be S 2, which is more than S 1. Again if we take the S 3, it will be S 3. So, in this way, if we can reduce the size. Okay. Now, here if we see with the smaller length, if we test, the mean strength will be, so L 1 and L 2 if we take, the mean strength will be S 1 plus S 2 by 2, because in this portion the strength will be S 1, next portion the strength will be S 2. So, the mean strength if we take, the strength mean strength will be S 1 plus S 2 by 2, which is numerically more than S 1. So, that means, if we reduce the size of the specimen for the same yarn, the actual the strength which is actually reported strength will be more, but the yarn is same. So, breaking strength is the load at break at the weakest point of a specimen of a specified length. Okay. Now, for length L 1, the breaking strength is S 1 and so on, S 1, S 2, S 3, S 4 like this. Okay. Now, with the gauge length of O dash, the breaking strength would be S 1, because it will break at S 1 point. When the test, we test 2 halves, so we can actually divide into 2 halves. One is O double dash, another is O double dash O dash. So, O dash we are dividing into 2 parts. In that case, we are getting S 1 plus S 2 by 2, because we are taking 2 values and then taking the mean. So, that is how, so we are getting S 1 plus S 2 by 2, which is numerically it is more than S 1. So, that means it is in any standard test method, as we have discussed when we are discussing the standardization of testing. So, the length of the specimen is specified. Otherwise, to show the higher strength, one would like to test the material at with a lower gauge length, and to prove that yarn is poor quality, you will start testing with the longer gauge length. So, that is why gauge length, effect of gauge length, specimen length is very important to be fixed. Okay. So, this specimen length and irregularity. So, hence, here if the irregularity is more, so the yarn is having higher irregularity, in that case S 1 and S 2, the difference of S 1 and S 2 will be more. So, if the irregularity is less, in that case S 1 and S 2 will be very close, that means the effect of fiber, the specimen length will be less. Okay. So, hence by testing yarn with shorter length, the apparent yarn strength has increased. Okay. This effect is known as weak link effect. So, yarn breaks at weakest point, and as we go on reducing the gauge length, apparent strength of the material will increase. Okay. So, for more irregular yarn, as I have explained, this weak link effect will be more, because the S 1 S 2 difference will be more. Okay. Hence, by adjusting the gauge length, the test result may be changed. That is why for any standard test, that gauge length has been fixed. In any testing, any tensile testing, gauge length is very important. Okay. It has got direct impact on the test result. So, standardization of gauge length is important. Now, you can say specimen length and irregularity. So, this is the regular yarn, blue one, it is a regular yarn, and this red one is a yarn with which is irregular. But if we see that this yarn with a higher mean length, mean strength, still the regular yarn with little bit lower mean strength is better. For processing point of view, slightly lower average length with regular yarn is better. So, that is why for particularly in weaving, for warp yarn, its irregularity is very important. So, we normally do not, it is difficult to measure the length strength irregularity, because strength value is there, strength C B is there. So, which one is important, strength C B or strength value? So, first for weaving, particularly in warp yarn, it is the strength C B which is important. So, two parameters are given, two yarn, one yarn is weaker yarn, little bit weaker yarn, but better strength C B. One should actually go for the better yarn, better irregularity with a little bit lower strength. Okay. Now, here this Peirce has given actually empirical equation. He has derived empirical equation which shows the effect of specimen length. Okay. Effect of specimen length on strength. Now, let us see carefully here. SL is the length of yarn, okay. Mean strength of SL is the mean strength measured at the gauge length L. Okay. Higher SL is at lower length. So, SL is actually mean strength of yarn measured at the length L, and SRL is the mean strength of yarn measured at length RL. what is R L? That is R times of L. Suppose if L is, say L is 10 its value, so 10 centimeter. So, R L, if it is R L is say 20, so R will be 2. So, 2 times of 10. So, S L is say S 10, suppose 10 at 10 centimeter gauge length, the strength is S L. At 20 centimeter gauge length, the strength will be S R L, where R value is 2. That means, the S R L will definitely be lower than S L always, because the gauge higher gauge length will result lower value. So, S R L is the value which is lower than S L. Okay. So, that means, this value will be less than 1, S R L by S L. So, S L minus S R L equal to 4.1 multiplied by 1 minus R to the power minus 1/5 multiplied by, this is the standard deviation. Okay. The standard deviation of breaking strength. The standard deviation of strength, okay, it is a sigma L. This formula has been derived by the, this is the empirical formula has been derived by Pierce based on large number of experimentation. Now, just by rearranging here, what we can get is the S L is the length, S L is the mean length, mean strength, sorry, S L is the mean strength of yarn at length L. Okay. Now, we divide both the term, both the sides by S L. So, 1 minus S R L by S L, and here this right hand side term will be that sigma L, that is your, it is a standard deviation by the mean strength, standard deviation of strength by mean strength multiplied by 100, it will be the CV percent. So, that means, it will that standard deviation by strength will be CV percent by 100, the CV percent by 100. So, this term, this has been rearranged in this fashion. So, this is the equation. So, here from there we can predict the strength at different gauge length. So, this is the term here. Now, here what we can see, S R L, as we have discussed, its S R L will be less than S L. So, the ratio. So, from this equation, if we just rearrange this equation once again, we will get this equation, that means, S R L by S L equal to 1 minus this within bracket 4.2 and this value. Okay. Now, here if we see what will happen if R is 1, suppose R is in this equation, R is 1 means is at the same gauge length we are testing, we are not changing the gauge length. R is R 1 means we are not changing the gauge length, R is 1 here. Okay. Now, what will happen, R is 1 means this value will be 1, okay, and this total value will become 0, 1 minus 1, this total value will become 0, that means S L equal to S R L. That means, for same gauge length it is predicted that the gauge length, if we keep gauge length, the mean length will be same. Okay. We are not taking care of other factors, here we are talking only specimen length. Now, let us see what happen if we increase the R L, R value. If we increase the R value, this R value, so there will be some positive value here, there will be some positive value. So, this value will be reduced, will be lower value. Okay. This, if we increase it from 1 to some other value, so this value will be, earlier it was 0, now what will be the value? It will have some value, some parameter, this value will be more less than 1. So, earlier it was 1, so it is less than 1, so that it will have some positive value. So, that means 1 minus some positive value. So, this value will reduce, okay. As R value R is increasing gradually. So, this value will also increase with the increase in R, this value will also increase. So, this right hand side value will reduce, will be lower. So, SL value will SRL value SL is constant. So, SRL value will reduce gradually. So, that means with the increase in R by SRL by SL will reduce. So, this we can get. So, if we know V and SL, one should be able to predict the SRL. Now, if the variability, we have seen the variability, if variability increases, that the yarn strength is reducing. Okay. Now, with this equation here we can see that suppose CU% is increased, if CU% increases, so this total value will increase, okay. That means this value will decrease. So, SRL by SL will also decrease. So, this ratio will decrease, SRL by SL, this ratio decreases with the increase in the R value, that is R value means, which means it is the specimen length, and the V value. V value is nothing but the specimen irregularity. So, with the increase in irregularity and the specimen length, this SRL by SL actually reduces. Okay. So, that means we get the lower strength, lower strength with the increase in the gauge length and with the increase in the variability. Now, another important parameter we will discuss, it is a rate of loading and time to break. So, the tensile characteristics, the strength of the material, it changes with the rate of loading. That means, at the rate at which rate we increase, rate of extension, rate of loading. So, that changes the tensile characteristics. Earlier we have seen with the change in the gauge length, the tensile strength changes. So, apparent tensile strength changes. Here also, if we increase the rate of loading and time to break, so then the tensile characteristics will change. So, most textile materials show an increase in breaking strength with the increase in rate of extension. Okay. So, with the increase in rate of extension, the breaking strength will it changes together with decrease in extension. That is the nature of any viscoelastic material. Okay. Textile material is one of the most important viscoelastic material. So, due to viscoelastic nature of textile material, they require certain time to respond to the applied stress. So, due to this, the rate of loading, it affects the rate of loading. Okay. Different type of textile material like fiber, yarn or fabric respond differently depending on the structure. So, but in general the structure is like this, it is called spring dashpot model. So, in the spring dashpot model, if we see carefully here, it has got two components. In this is the simplest model where these are in parallel, spring and dashpots are in parallel. The spring equation is that spring, when we apply force F on the textile material, this is suppose it is a model for yarn or any textile material. So, here it is any textile fiber also. So, here if we apply force, it has got two components, F1 component which is actually represented by spring, F2 component which is by dashpot. So, for a spring, the equation is that force increases with the extension. Suppose we are extending by x. So, the force increases with the extension, force is proportional to the extension. So, here F equal to K1x, the K1 is called spring constant. So, as we increase the extension, so the force will increase, it is a proportionally. But in case of dashpot, what happened? The equation is the force increases, but with the rate of increase in rate at the rate of extension increases. But in case of dashpot, if the rate is very slow, rate is low, then dashpot will actually exert very low pressure. Okay? So, if it is very low, then force will be very less, but as the rate increases, the dashpot will actually exert very high force. So, that is due to this dashpot. So, this K2 is dashpot constant. So, it is proportional to the dx dt, that is the rate of extension. So, as the rate of extension increases, so due to the F2 component, the textile material actually exert more force. Actually, that is why the due to the increase in rate of loading or rate of extension, the tensile characteristics, apparent tensile load increases. Okay. So, this picture shows that the rate of at lower rate of extension, this is the curve, and the same material with the higher rate of extension, it has become stiffer and it shows higher strength. Okay. Now, we will stop here, we will continue with this discussion in the next class. Thank you.